A key component of the modern world economy, the chemical industry delivers products and innovations to enhance everyday life. It is also an industry in transformation, where chemical executives and workers are delivering growth and industry-changing advancements while responding to pressures from investors, regulators, and public opinion. Discover how leading companies are approaching these challenges here on The Chemical Show. Join Victoria Meyer, president of Progressio Global and host of The Chemical Show, as she speaks with executives across the industry and learns how they are leading their companies to grow, transform, and push industry boundaries on all frontiers. Here's your host, Victoria Meyer.
Hi, this is Victoria Meyer. Welcome to The Chemical Show. Today, I am speaking with Trevor Best, who is the co-founder and CEO of Syzygy Plasmonics. Syzygy is a technology startup that's using a breakthrough plasmonic science developed at Rice University to perform chemical reactions. They're developing chemical reactors that use light and change the energy profile and the CapEx profile of typical chemical reactors. So we're going to be talking with Trevor all about this, about being in a startup, about how they're getting to commercialization, et cetera. Trevor, welcome to The Chemical Show.
It is fantastic to be here, Victoria. Thank you so much for having us.
Yeah, absolutely. Delighted to have you here. What's your origin story? How did you get started in chemicals? And then how did you turn your focus to green chemical manufacturing and what you're doing today?
Yeah, thanks for asking. So, my foray into startup land goes all the way back to 2013, and at that time I started trying to get something off the ground, and I just wanted to do good. The first one was a nonprofit called H2 Open Source. That one didn't work out, and as things went on, tried other things focused around water purification. That was a company called Matabios, and that was where I met my co-founder, Dr. Suman Kadiwada. And then when Suman and I first paired up, we were working together at Baker Hughes in their R&D division, and we had decided hey, we're going to change the oil and gas industry and push it towards green energy from the inside out. And this was 2015 or so. It was a bit ahead of the time.
Yeah.
And we realized that if we were going to help to enable an energy transition or something, we needed to do something really bold. So Dr. Kadiwada and I actually went on a technology search, and we were looking at a lot of different technologies coming out of different universities like MIT, Stanford. And in late 2016, I think August 2016, the two professors, Professor Naomi Hollis and Professor Peter Nordlander, our co-founders at Rice University, released their first paper on the plasmonic antenna reactor photocatalyst. Dr. Kadiwada and I are very inquisitive people, so we went and started talking to them once a week about the technology, doing diligence on it. And when they started telling us about some of the numbers that they were achieving, and we started comparing that against traditional catalysis and especially traditional photocatalysis, and we see that this thing is outperforming what had been done in the past and what's done in industry today by orders of magnitude. We were like, oh my goodness, there's something here. So 2017, decided to leave our jobs at Baker Hughes and go all in on the company. Both Dr. Kadiwada and I cashed in our life savings and did the whole startup launch, two guys in a basement. And with the help of the professors from Rice and a number of other angel investors around town, got it off the ground, and the company formally opened its doors in just a week from now. So it was February 5th, 2018. And so in 1 week, we'll have our 5-year anniversary.
Wow. That's pretty amazing. And really 5 years from formation to where you are is actually pretty quick in the startup world, especially technology startups.
Yeah, we are moving blazing fast. And how we got into chemicals, it was a bit of a fortuitous thing. We were looking at all different kinds of things, solar panels. We were looking at different kinds of, thermoelectric materials and other things that could help enable the energy transition. And, we just picked this one, not knowing much about chemistry. And when we started really digging in and doing the diligence, looking at like what the future would look like, we saw the importance of hydrogen at that time. Like, oh, if we're actually going to decarbonize, hydrogen has to happen at some point. This tech we found could potentially change, the fundamentals, change baseline for these major chemical reactions planet Earth needs. And let's start with hydrogen because that'll happen sometime. And we called that shot in late 2017.
Wow.
And yeah, and hydrogen was, I wouldn't say it was a dog. It was already $100 billion industry, but it
But it's
wasn't
kind of
until
an
like,
old school industry, kind of, utility, really viewed as a utility for a very
yeah,
long time. Yeah.
very much so.
Yeah.
Yeah. And
What's okay. So, Trevor, like, I don't personally just go out and look at like technology applications and patents and coming up with these things. So, so it takes somebody special to want to do that. Were you working in two things? Were you working in a really technical space when you were at Baker Hughes? And Baker Hughes does a lot, obviously, with oil field chemicals and chemistry and stuff. So was this also a natural tie to be looking at chemicals based on your experience at Baker Hughes? Or was it really just this leap into the bigger picture, doing something new?
it wasn't that big of a leap. I had said both Dr. Kadiwada and I worked in the R&D division. And so I was actually the quality manager for the invention process. So like I oversaw like how the process by which like we get ideas, out of people's heads and onto paper and
Yeah.
make one in the lab. And then the export to supply chain piece is where a lot of problems would crop up. And so like as the quality manager for that process, I would go in and fix it when it broke down. And so I had this really macro level view of how R&D was done and how projects were run. My co-founder, Dr. Kadiwada, he a PhD in nano engineering from Rice University. He was one of the material science. He's actually the one writing the patents. He understands like what happens at the atomic level with these things. In my role, I also got quite technical. I needed to know how the equipment worked to understand how to manage it. And so, we were both pretty technical starting out. And a lot of the, things that happen behind chemical engineering is like, metallurgy and, mechanical design and
Yeah.
energy transfer and the really scientific piece, the catalysis, and especially the photocatalysis. That's why the two professors from Rice University, Professor Hollis and Nordlander, are also co-founders because they are world-renowned plasmonics experts. We've hired people out of their lab like Hossein Robot Jazi. He's over our catalyst development now. We worked with him way back in the day too, and he was part of the Hollis lab. And as we've grown, he left the Hollis lab and joined us. And he really knows that science. Our first hire was a PhD chemical engineer, Dr. Shreya Shah. She really knows chemical engineering. So really from the get-go, we had a pretty strong technical basis.
Yeah, it sounds like that. And yet you've had to become a very commercial person in order to lead this organization forward.
Oh yeah. And basically the deal between Suman and I is he makes the reactor work, I bring in the customers and the money.
Okay.
I'd done a lot of public speaking whenever I was younger. I used to do like debate and theater and stuff like that. So I kind of take to it naturally. And I also
Yeah.
had a Six Sigma black belt in Baker. So I would have to get into like organizational architecture and like why do processes break down, and that pretty broad toolkit to draw from.
Yeah, that's awesome. That I think we may come back to some of that in a little bit, but let's get into Syzygy. So you kind of touched on where it started. What is it and where is it today? And maybe you can even just start with the name. What does Syzygy mean? And then plasmonics. What does that mean? And why are you, where is it today? What is it and why is it here?
Yeah, so starting with the name Syzygy, I know, very funny name, but serious science. Real English word. If you can land it in Scrabble, you basically win.
I'll have to keep that in mind. All right, cool.
Yeah. But what it means is the alignment of three planetary bodies in like a straight line. And a really good example is an eclipse. So when the sun and the moon and the earth line up during an eclipse, that is a syzygy. And it could be Earth and like Saturn and Jupiter, but anytime three three planetary bodies line up. For us, it means the alignment of three things that are shaping the future: energy, technology, sustainability. Where those three things line up, you get Syzygy.
Cool. And then what is plasmonics?
Yeah, so plasmonics is a field of science, and this is kind of a subset of nanophotonics. So nanophotonics studies the interaction of light and matter at the nanoscales, and then plasmonics is some metallic or some metal, aluminum, copper, silver, gold. These are the plasmonic materials. When you hit them with light, especially when you make these nanoparticles out of them and you hit them with light, they will form what is called a plasmon on their surface. And basically it catches the photon, and all the electrons on the outside of that metal get excited and start jumping around, and we can use those to do work. And so that plasmonic effect, we are using that to drive chemistry. It can do other things than chemistry, like the professors. They also have another company called Nanospectra, and they're using the plasmonic effect and these nanoparticles to actually fight cancer. They recently treated the local weatherman, Frank Billingsley. They treated his cancer not too long ago in a success, but kept developing it, got into catalysis, and now we are using plasmonics to drive catalysis in a new way. And this is pretty much like cutting edge science. It wasn't really known how to do this well until the past couple years, and the professors made this breakthrough. And basically, if you build these structures in some way, it's not that exciting of results. But if you build them in a very specific way, suddenly there's just this like exponential increase in a lot of the metrics that matter for chemical engineering.
Yeah. So what's interesting about that is the chemical industry does not typically embrace cutting edge very easily, right? And so you've started Syzygy about 5 years ago. You're obviously rapidly developing. You've got some partnering, and yet, let's be honest, this is not an industry that wants cutting edge. They want tried and true and proven. So how are you resolving that, right? Because as you try to get into this market, it's not easy to get in with something brand new.
We are resolving that with a tremendous amount of effort. But really, I think the key for us has been radical transparency. And when we think about like our field of science, like plasmonic catalysis is kind of this subset of photocatalysis. It is not a field of science that has worked historically for the chemical industry, and this is not for a lack of trying. And in fact, almost everyone we meet has or knows someone who like did photocatalysis, whenever they're in academia or worked on some photocatalysis project with like an energy major or a world government, and it has never really panned out. And so now that we are getting some like really impressive results, the biggest response we get is, BS. So how we've managed to get over that is, basically bringing people out to the lab. Like actually just in a room right over there, we have a reactor museum where we have like all the versions of the reactor since we started the company. So you can actually like see, how we've progressed, and you can see pretty clearly like how it works. And that kind of transparency about like, this is what is happening on the inside, coupled with, the results we're getting, has, been able to win people over. And I think that the past couple of years, the push of the energy transition and uncertainty about the future has also made everyone a little bit more risk tolerant. And so if we tried to do this a decade ago, I don't know, it would have been tough.
No, I think the industry wasn't ready. And as you say, the energy transition, the focus on sustainability, net zero, et cetera, has driven a race to innovation and the acceptance of new technologies in ways that we haven't seen in the past several decades. So that totally makes sense. So let's get maybe into a little bit of the actual technology and maybe your objectives with it, right? So at the end of the day, and before we got on and hit the record button, you were really describing Syzygy as an a chemical equipment company. I think you have a better way of saying that. But where is Syzygy going, and what is the vision and the future of Syzygy?
Yeah, so we are a chemical process licensor. So if you want to think of companies that are similar to us, this is like your Halder Topsoes, your Lummus Technology, Honeywell UOP. So you develop the core tech for making a chemical transformation happen, and then you have to partner with a lot of people like EPCs, the operators, other, component sub suppliers and things like that to actually deliver. And so we make the chemical reactor. We help to design the package and the interface that goes around it. And then we license that technology to someone else for them to use. They pay us a little bit of money for the license, and they also buy the reactors and the catalysts from us.
Got it. Got it. And the reactors are glass. Am I right? And so is this the big deal, is that it's using light? So is it using ambient light? Is it using focus light? How does that part work?
Yeah, so there is a big piece of glass inside the reactor. So if you were looking at it from the outside, it's not like, Crystal Castle, like this solid glass structure. No, the outside is like, metal. And we're able to generally build out of low cost materials since we operate in a different way. We don't need quite the pressure temperature that others do. But so we have the light sources. We're using LEDs today. We've been experimenting with a lot of other interesting light sources to energize the catalyst. And between the light source and the catalyst, you need a piece of transparent material. Like right now, we're using quartz, and that will let the light through to interact with the catalyst. And it's also pretty interesting because those materials are generally pretty good insulators. So they're good at keeping energy in. And that kind of method of directly delivering energy to the catalyst is very different from how people do it today. Today, they have a burner which heats up the whole chamber. And we basically just beam the energy right to the catalyst bed.
Interesting.
Yeah. But
different.
Just to give people a picture in their head, you can imagine a quartz tube, and it's pretty thick. Like we're talking multiple inches, and it's, about the size of a person. And that is the heart of our reactor.
Huh. Okay. So it's different than I had personally envisioned it being. That's good to know. Okay. So you guys are starting with hydrogen, right? So it's a very large market, large assets. As you noted earlier, it's kind of had been a pretty sleepy market, if we will, right? Viewed as old technology. But it's also technology that's at a high scale, high energy usage, large scale options. Why did you start with hydrogen? What's it with hydrogen? Why did you start there? And I think, even just from a scale perspective, how do you get to scales that make sense?
Yeah, so hydrogen was a pretty clear choice from the beginning, just because, we started the company to decarbonize and basically prevent combustion, allow these operations to run on renewables. And when we're looking at how do we help decarbonize, and we're doing the math around, I think people are starting to get a lot more familiar with this, the LCAs and life cycle assessments for carbon intensity. When we're doing these back in 2017, we're seeing the importance of hydrogen to a future clean economy. It does not happen. We would love to run everything on electrons or renewable electricity, but you can't have society without molecules and molecular energy, and hydrogen is a critical feedstock. It's an energy source. It's this Swiss Army knife that has no carbon atom attached to it. And so just from the market case for it, there's a market there today. There's a huge scale market. There's a healthy, small scale market, opportunities for fuel cell vehicles, opportunities for energy and feedstock for low carbon operations. It was we have to start with hydrogen. And and sorry, what was the other question?
So then I guess, how do you get to scale, right? So obviously with a new technology, you're starting small, relatively small, How do you get to a scale that makes an impact, especially when you think about hydrogen as being such a large volume market?
Yeah, so scale's been fun. As we took it out of Rice University, we started very tiny. We're talking like, millimeter sized catalyst pellet that is making milligrams of hydrogen per day. You've made a couple jumps. Right now, we're operating at a scale of can max out at about 20 kilograms of hydrogen per day. The reactor is a little bigger than my head.
Okay.
And we're in the process of building out that first one that is around the size of a person. And that one will make about 200 kilograms per day. And that one is called Rigel. That's the name of our product, the Rigel reactor. Rigel is a
Awesome.
really bright star in the Orion Nebula. Syzygy is an astronomy term. We're kind of space
Yeah.
nerds.
Playing off of that. Yeah, absolutely.
Yeah. So Rigel is about 200 kilograms of hydrogen per day. And then you put multiple of those units together into reactor banks. So let's say you have 5 together, that does 1 ton of hydrogen, 10 together would do 2 tons. And then it is just how many banks do you need for your application? And so similar to the same way that like electrolyzers scale or batteries scale or solar panels scale, like cellular modular methodology. It's just that our cell, a Rigel reactor is kind of like a cell. It's just really big.
Yeah. Yeah, that makes sense. So it's really the end game is a modular system that you put together as many pieces as you need.
Yep.
Yeah. Awesome. So I know that per your R&D roadmap, 2023 is the year of commercialization, which is always a big pivot point with startup companies as you move from really this development and very technical focus into commercialization. What does commercialization mean, and what does it look like for Syzygy?
Yeah, so this is probably the biggest transition we're going to have to go through as a company. And like
Yeah.
up until this time, we have been this R&D company, and you're managing everything for Eureka. And when you're managing the company so that someone inside can achieve like a Eureka moment and like come up with a new design that like improves the metrics, and
Yeah.
you have to manage in a certain way. And then now we're no longer managing for Eureka. We know what to do to hit the numbers we need to be disruptive, but now it's like execution and like timelines and project planning and budgeting and all these fun like traditional company things. So we're doing a lot of initiatives to kind of push the company and change it from an R&D company to a product oriented company. Like we're hiring a lot of people who have a lot of experience in the industry in different functions. We're really growing out the other groups like our operations, G&A, like HR and accounting groups, sales groups, etc., bringing them all in and kind of like indoctrinating in what it means to be a part of Syzygy. We call ourselves plasmon, so like what it means to be a plasmon. And that is all preceding the actual like technology delivery. So right now we're building that first commercial unit, that 200 kilogram per day reactor. We're going to test it at our facility this year, and then we get to deliver it to customers who we've signed agreements with. And so test it, get a learning cycle in, deliver it to customers, let them test it, see how it works. Those customer tests should be happening around end of the year. And then everybody gets to see the data, things are looking good. Then we level up again and we start getting orders for the banks, or multiple of these together, where we actually start producing at scale. So timeline, testing a single reactor, like one of those Rigels this year at our facility, and then at customer locations. Next year, reactor bank, at customer locations. And then 2025, we can actually start like bid processes for building a whole refinery, kind of giant scale facility out of our tech. And talking about moving fast, like for this, that is just blazing fast for a new tech in this industry. I think
it really is.
I think we're setting records. I don't know, but maybe.
Yeah. So I recently, or last year, I talked with Jennifer Holmgren from LanzaTech, and it's, LanzaTech has it's received great notoriety. It's seeing a lot of success. And they've been at this for 20 years to get to this point. So it's easy to say, oh, it's an overnight success because I've just recently heard of it. But in the case of LanzaTech, it's taken them 20 years to get to this point. So I think you're right, Trevor. I think you guys are moving blazing fast, maybe at the speed of light, if we could even say that.
We like to make a lot of jokes like that. Yeah.
I'm sure you do. So you started talking about customers. Who are your target customers? When you think about, as you guys are selling your technology and selling these reactors and the components that go along with it, who are you targeting?
So I'm going to talk in general, and then I'm going to talk like about some of our specific projects, and then I'd love to talk about, our customer base or strategic investors who have like come in and will probably be our initial customer base. So like in general in the market, we're targeting like the large energy companies, operators. We can do many different chemical reactions. We can do hydrogen from ammonia, we can do hydrogen from methane, we can do CO2 to fuel. And these are all very important reactions for a clean energy future. And those operators, the Chevrons, the BPs, the Equinors, like they are the ones who are most interested in these reactions. They make the fuels, they make the methanol, they sit in that energy nexus. And there are some other interesting parties like vehicle manufacturers like Toyota looking at hydrogen vehicles, and other like conglomerates like we are also very involved with like Sumitomo Corporation and Lotte, and those like industries are more like trading companies where they have sections that play in energy, but they're much more diversified. And so very broad stroke. And the reason being is because to get one of these big projects done, you need a lot of parties. You need engineering partners, you need operators, you need off takers, you need capital providers, you need government support, you need just so many people involved to get one of these projects done. And so we're making a lot of effort to bring them all to the table. And we bring our piece, and then others bring each of their pieces. So the projects that we have ongoing right now, we've got 3. So one is, and the first one we announced in August of last year, that is with Lotte Chemical in South Korea. So we'll be, deploying our technology with Lotte and also in conjunction with Sumitomo Corporation in Ulsan, South Korea. And this is for ammonia splitting. So they envision bringing in lots of clean energy in the form of ammonia to South Korea and use our technology to split it and get the hydrogen back out.
Got it.
And the next project, this was actually just announced 2 days ago. This is a CO2 to fuels project, and it is sponsored by Sumitomo again, and also Equinor. And under this project, we're taking in CO2 and methane. We are turning those into syngas, feeding them to a Fischer-Tropsch reactor, and ultimately making sustainable fuels with the end goal to be like a pathway to make SAF at a very reasonable cost. That reaction is especially exciting because it has the potential to compete head to head with traditional fossil fuel, like straight up like traditional gasoline or traditional jet fuel, compete with it on price while having a much lower carbon intensity. And then the third project is ammonia splitting, similar to the project in South Korea, and this one is in California. We have not done any press on that and probably won't, but we do have a project looking at California and that kind of like energy importing in the form of ammonia and then turning it back into hydrogen for different applications.
Awesome. I think that's good. So, I mean, obviously partnering is really critical in this space. So, I mean, and you guys have, it seems like you found some really good partners to work with. What makes a good partner for you? What makes Syzygy a good partner? How do you guys look at this whole, because obviously there's always an array of companies and individuals you can partner with. What's been critical to you as you've progressed with that?
Yeah, so I mean, we're very concerned with scope, and scale. So like how big of a partner can they be? Someone who can like deploy meaningful amount of reactors, like actually impact like meaningful change in terms of carbon emissions is first and foremost. After that, like I'd say a willingness to change. Like, are they actually serious about this? Do they actually want to make the transition happen? And I'd say those are the two primary ones.
Yeah.
And you can look at our current partner base, and we've done quite well. We have picked up Equinor, Chevron, BP, Saudi Aramco, Toyota, Latte Chemicals, Sumitomo, and Pan American Energy. And so, lots of very committed partners. And I think that this group is, especially when you talk about the energy companies, there's like a whole thing like, is the energy transition really going to happen?
Yeah.
And one of the things is that with this group, like they actually gave us like access, pretty high up in the organization, and we got to have conversations, and like they have all decided that something is going to happen. Like the energy transition is going to happen. They are going to decarbonize, and they are all very much like looking as like which technologies can actually do it.
Yeah.
And yeah, so very much like, can they deploy at scale, and are they actually going to do it, are our main criteria. And we feel that we've done pretty good.
Yeah. That's awesome. It sounds like a great set of partners, a great list of names that you guys are working with. I know they're excited to be doing that. One of the other questions I had for you is really around scale and speed, and you've touched on this speed, and you guys are moving really quickly to get to a commercial platform. What lessons are you taking from other technologies or digital companies in terms that seems to have mastered speed and scalability? Like, right, if we look at Silicon Valley, they would at least have us believe everything's fast. What lessons have you taken from that, and how have you applied it to what your company is doing?
So I love other founders, and I talk to a lot of other founders, like pretty much as many as I can meet, and some very successful, some earlier stage than us. And especially when talking about like software in Silicon Valley, a lot of those companies can scale in ways and at speeds that I just don't know if it's possible for a company like ours to scale. I'll talk about some of the key learnings here in a second, but like when you're looking at a chemical technology like ours versus like a software company, if a software company has a critical failure, they delete some congresswoman's or congressman's Twitter account, and sure, they're upset, but like it's not that bad. If we have a critical failure, it is pretty serious, pretty
Right.
significant. So we can't move too fast. We have to make sure that we have a lot of rigor, a lot of checks and balances in place as we get to larger scales. And it takes time. And even like we're working with governments on like permitting, especially with a new technology they haven't seen before, that doesn't move as fast as you would like it to. But I think that some of the key learnings is build for the next step. Like wherever you're at, always be building for what comes next. Because if you wait like until you're 100% ready, like if you've done A and now you raise money and then you're supposed to go do B, start building for B before you've got the money raised. Otherwise, there's like this cycle after you get the money in where you have to start to scale, and it like stalls out. So if you want it like smooth progression, you always have to be building for the next step. Treat your people well. Like you are only as good as who you have on the team. And yeah, it is like I have the easiest job in the whole company. I really do. I just sit here and I talk about all the awesome stuff that everyone else does. And like when we talk about like achieving these milestones and bringing customers on and getting recognition, like that is a tremendous amount of work by everyone around me. So
Yeah.
Treat your team well, surround yourself with good people, and you will go far.
Yeah. That's awesome. That's awesome. So Trevor, I think we've touched on some of this already, but what's next? What should we be looking forward to from Syzygy?
So what's next for us? We've got the money. Now we need to go deploy in the field. And, it is very much like on us to execute. So we got to get this technology, tested at our facility. We got to get it deployed in the field. We got to, hit the metrics and milestones that have been set before us, and then the sky's the limit.
Awesome. Well, great. Trevor, this has been fun. Thank you for joining us today on the Chemical Show. Appreciate having you here.
Yeah, awesome. Thank you so much, Victoria. This is a fantastic pleasure.
Absolutely. And thanks everyone for listening. Keep listening, following, sharing, and growing the Chemical Show podcast. We'll talk to you again soon.
We've come to the end of today's podcast. We hope you enjoyed your time with us and want to learn more. Simply visit thechemicalshow.com for additional information and helpful resources. Join us again next time here on The Chemical Show with Victoria Meyer.